Welcome back friends for another edition of quantum field theory and quantum entanglement. So we were starting with we started with the quantization of the electromagnetic field, and we were looking at the problems associated with it. So the couple of problems we saw was that we are starting with 4 fields. Okay, so we have a mu which has A0, A1, A2, A3. So it is like a combination of 4 scalar fields. Okay, so it's like you have 4 fields which have to be meaning quantized essentially in equal, each of them, like each of them has to be quantized like what we did for the scalar field. You have to find its momenta, conjugate momenta, and impose equal time commutation relations and so on. So we did the similar thing also for the fermionic field, but it was different. We had to use quantum. There was a different complication associated with it, which is essentially the using, instead of using commutation relations, we were using anti-commutation relations because of the spin. Now, in this case what happens is that you have 4 scalar fields because it is all bosonic field theory still, but it is spin 1. The other complication which we have seen is a couple of complications which we have mentioned yesterday, is that if you try to find A0 dot, okay, I will explain, and this is vanishing. Okay. So in particular, so if you have A0 at any time, if you know what is A0 at any given, and A0 at given the boundary condition of the boundary condition of A0, so you can solve for A0 meaning at any other time, essentially at some time. So the evolution or what happens to the A0 at the other times is not dependent on A0 essentially. In principle, what happens is you can use at some time t, it does not evolve. So the A0 is completely determined because it does not evolve, essentially it is completely determined. So what happens, okay, now what do you use to determination? So you use, you remember that we impose okay, so E is equal to minus del phi minus del A bar by AT, okay, and we have the equation del dot E is equal to 0, okay, and del dot E is equal to 0. Okay. So using this relation essentially, okay, equation of motion in the absence of sources, so until I mention sources, I will leave it as it is, we are not considering sources. So which you can expand this del dot E is equal to 0 and use this expression, and this gives me del square A0 from this equation essentially plus del dot del A bar by LT is equal to 0, and this can be solved essentially for the A0, and this is given by A0 of x, say for example. Now okay, this is obvious that the cube of x prime, say for example, and del dot del A by dt, okay, this expression whole thing of x, okay, and because the Laplacian solution you can put in this expression essentially for x minus x prime, okay. This is just the Laplacian of so the Laplacian of A0 you can really solve it as this, taking it on the right side and then solve it, taking it by this thing essentially. So this expression has this this can be solved, the formal expression, but the important point to note is that A0 is no longer independent. Independent degree of freedom, it is determined completely by A bar. Yeah. Completely by A bar, meaning which is the three component part of the A0. So that means you have one redundance degree of freedom. Okay. So one degree of, but actually it is not actually the reason, like we mentioned, the quantization of the A field or the A mu field quantization leads to photons. Okay. So, but photons have only 2 degrees of freedom. Okay. Only 2 degrees. So, that means even 3 degrees of freedom. So, A bar itself, say for example, now you are saying that okay, there are no 4 degrees of freedom A0, A1, A2, A3, but instead A0 is completely determined by A bar. But then even that is large because you have 3 degrees of freedom. So, only 3 degrees of freedom you can say here, 3 independent degrees of freedom, but that itself is more. Is also large because the physical degrees of freedom of the photon are only 2. Okay. The physical degrees of freedom are only 2 essentially. So, what is the cause essentially? What is the other cause? So, one can, this is an important thing which is called the gauge symmetry. Gauge symmetry. Now, you know that if you have a mu of x, now you can always transform it a mu, it is only determined up to del mu of phi. So, some phi essentially. So, but since we have used phi, let us call it as lambda of x. Okay. So, you can always change a mu with a derivative of lambda of x. Lambda is some field, some scalar field, and then nothing changes. Essentially, the equations of motion or the Maxwell's equations, none of them can determine a mu completely. They can only determine up to a mu plus del mu lambda of x essentially. The equations of motion, okay. There is some condition that lambda of x, the gauge parameter, the lambda of x should go to 0 at large x essentially. So, okay, to just to mention essential condition, lambda of x tends to 0 at x tends to infinity. Okay. So, lambda of x tends to 0 at x. Okay. Now, this symmetry now this symmetry is not like global symmetries like what we have seen, like quantum numbers like lepton number or electric charge or any of these global symmetries which we fix by Noether's theorem essentially. Okay. This is not gauge symmetry. Gauge symmetries are much more subtle. The point is that the equations of motion which are essentially the Maxwell's equations essentially, or do not completely fix a mu. That means they can only fix up to a mu plus del mu lambda x. You can also see because that is the reason, because f mu nu prime, f mu nu, okay, under this gauge symmetry, say for example, you have okay, let us define remember what is f mu. F mu is nothing but del mu a nu minus del nu a mu. Now what happens to f mu nu prime? F mu nu prime is given by this goes to essentially del mu a nu plus del nu lambda of x, okay, minus del nu a mu plus del mu lambda of x. So, under this gauge symmetry, this is, if you expand this is nothing but f mu nu. So, under the gauge symmetry, f mu nu is invariant essentially. F mu nu okay. Under this gauge symmetry, f mu nu is completely invariant. So, now that means that you cannot determine by solving f mu nu, meaning taking the derivatives of f mu nu and the Bianchi identities completely. The a mu is cannot be completely fixed essentially, but we take the approach, say for example, one can take the approach that you fix a mu plus delta lambda of x essentially. That means you want to treat okay, to be more accurate, what we should say is that a mu and a mu plus delta mu lambda of x represent identical states. This is the main crucial point. That means that a mu, okay, a mu and a mu plus del mu lambda of x represent identical states. That means if you quantize these things and if you quantize a mu prime, they represent identical states. They don't, there is no difference between these two states, okay, there is no difference between these two states, and that is the reason why we are having this problem with the degrees of freedom essentially. So, gauge symmetry is like a redundancy. So, gauge symmetry is a redundancy, okay, which has to be dealt somehow, meaning you have to treat it okay, we will see the methods to fix this thing. So, that means it has redundant degrees of freedom, essentially there is large number of meaning. So, imagine that there are large number of as it is true for a large number of lambda. That means you have you can take lambda to be anything, you have a choice of functions which are large number, so infinite number of these things. So, you are introducing infinite meaning that means there is a redundancy of infinite order essentially in principle essentially in determining a mu. So, you have an redundancy of the order of the infinity essentially. So, Maxwell's equations are not sufficient to fix okay, a mu, meaning a mu, okay, that because the equations of motion in eta mu nu del rho minus del nu acting on a nu is equal to 0. Now, this function, these equations actually okay, they are non-invertible essentially. This is non-invertible invertible. Okay, this is non-invertible. That the basic idea is the equation of motion is, see, one way of thinking it is that the equation of motion, the inverse of the equation of motion is nothing but the propagator, right? Essentially that is your propagator. Now here this itself is not invertible essentially because it has a its inverse is not defined because it is not definable because it has it is a matrix. It has a rank, this rank essentially if you calculate this is a matrix of the rank, say for example it always has a 0 eigenvalue essentially. In other words, if you want to call it as a, if you construct a matrix of this type, it always has a 0 eigenvalue. That means you cannot invert this, its determinant is 0. Okay, its determinant is 0. So you cannot invert this kind of a matrix. So its determinant is 0, it's non-invertible. So and also any del phi, any del mu lambda is annihilated. Okay, any del mu lambda is I mean in this equation you put in any del mu lambda in this, it just goes away essentially. So the basic idea is that but then you can say, why don't I don't use then why do you choose A, why do you choose A? Why don't you work with E and B fields? So why not work with E and B fields directly, because they are gauge invariant and then you do not have to worry about anything. But not all phenomena are explained by the physical. See, E and B fields are physical, local and also gauge invariant. So one can ask, why don't you use these fields to quantize, but they do not describe all phenomena. All phenomena, okay. And further, as we will see, we want a Lorenz invariant description. Essentially, we also want and further we also want a Lorenz invariant descriptions. Okay. So they do not describe, for example, the describe which they do not phenomena. I think what the phenomena I have in mind is say Aharanov-Bohm effect, which is best explained in terms of the gauge fields essentially. So if you have some phenomena like Aharanov-Bohm effect, it is not explained by considering E and B fields. You need to consider the gauge field essentially, the A field, and that is the only way. Okay. And also we want a Lorenz invariant description. So the Lorenz invariant description is in terms of this these A fields essentially, this the okay. So how to move forward? The way forward is to fix the gauge. That means okay, so you can so there are several gauge meaning there are several meaning the gauge parameter can be large number of fields. So you can think of some gauge orbits, like for example if you want to, okay, so you can think of some gauge orbits, meaning you can gauge fields you can take, it can take in any parameter. Say for example you can think of gauge orbits for this like this. So gauge orbits will be like this. So these are lambda, lambda, lambda. So various lambdas 1, 2, 3, 4 something, but you then you fix it. okay, you fix the gauge such that then the redundancy is reduced essentially. So, the redundancy is removed. And then you can quantize it, and but then okay. So, the way forward is to fix the gauge essentially, that is the basic idea. So, these electromagnetic fields keep lying in the we are starting with very redundant degrees of freedom, redundant electromagnetic fields are described in a redundant fashion, but then you reduce the redundancy by fixing the gauge essentially. Okay. So, these are called, now the problem is fixing the gauges is also a lot of possibilities are there, okay, then quantize. So, but there are many choices. So, we will see one of the okay, let us see a couple of choices essentially. So, one of them is not completely Lorenz invariant, and the other one is Lorenz invariant. Okay. So, there are two choices. Okay, let us consider there are actually many choices. There are axial gauges and non-axial gauges and so on. So, essentially, so let us look at two important gauges which we will consider. So, one of them is the Lorenz gauge. This is the main gauge, okay. This is the most important gauge, and in the after a small detour to Coulomb gauge, we will be most of the time using this gauge essentially, we will be using this gauge most of the time. Okay. Okay. So, now okay. So, we can always pick a representative, we can choose a configuration which satisfies this thing. We choose a configuration of A mu which satisfies this. And such a thing is possible, because imagine that if you if you are given something like del mu A mu prime is equal to some f of x, okay, let us say if A mu of prime is f of x, then we choose A mu is equal to A mu prime plus del mu of lambda, okay, and del mu of m. Now, if somebody is given, okay, suppose if this gauge condition is not satisfied, suppose this is not 0, but somebody gives me f of A mu of prime is equal to f of u, but then you can choose the choose a gauge parameter lambda, choose okay, such that you can define this, and then you can have del mu lambda is equal to minus f, such that del mu A mu is equal to 0. Okay. Now, if you put del mu on this, and you get del mu lambda is equal to minus f and cancels essentially, and so you still have. So, you will always find, one can always find solutions solutions or configurations of A mu which satisfy this. So, the entire point is that this choice is a good choice, because even if somebody gives you another configuration, we can always fold it into this configuration by a gauge choice essentially. That is it's yeah. Now, this is the most important gauge, and the main thing advantage is its Lorenz invariant. Okay. Good. So, we can always find solutions or configurations which satisfy this. This is an important gauge, and now let us move to the other gauge. The other gauge is called the Coulomb gauge. This is also another important gauge. Now, this gauge is defined by del dot A bar is equal to 0. Now, this okay. Now, what we can do is that given this choice, this is also an important gauge. Actually, it is used in some calculations. Whenever it is convenient, one chooses the Coulomb gauge also. Essentially, it is an important gauge. Given this choice, what does it do is that you can always make the thing, okay. What we can do is, given this choice, one can use residual gauge choice. So, the residual gauge choice is meaning what you have is this thing. So, you have okay, you have so that now del dot A bar is we had set fixed to be 0. Now, you have A0 of x bar given by this thing, no, d cube of x prime del bar dot A del t of x prime. You remember the Laplacian, by this equation essentially. So, it is fixed by this thing del dot A. Now, you can interchange del and derivative of the time essentially, and then you can choose, okay, what happens is it has this consequence A0 in this gauge is equal to 0, and this is useful, very useful sometimes essentially. Okay. For some calculations, this kind of okay. Now, this is very useful sometimes, especially okay. Okay, there is a caveat for this thing, because this is all in free phase space essentially, in the absence of charges. Okay, this is not true in the presence of charges. Note that this is an important note essentially. So, I should be careful when I should not oversell this. So, this is okay. This is not true in the presence of charges. Now, this is useful in sometimes actually. There are many cases in which the Coulomb gauge plays a very important role. Meaning when the choice makes it useful to calculate essentially, and it simplifies the calculations, because especially when there are no external charges and currents and everything. In some cases in field theory this is useful, but most of the time given this gauge choice, is given this gauge choice is not Lorenz invariant, for most of the quantum field theory applications it is not really very nice essentially. Most of the time given this gauge choice is not Lorenz invariant, this is not very useful, especially when you are looking at higher order corrections and stuff like that essentially. So, it is not a very useful choice, but it has some advantages. Say for example, because A0 comes out to be 0, you have del dot A is equal to 0. So, you can see that the main advantage of this is that you see that this shows that only 2 degrees of freedom. Okay, let me write it separately. So, these two choices, say for example A0 is equal to 0, A bar anyway A dot is equal to 0 and del dot A bar is equal to 0. This means that there are only 2 relevant degrees of freedom, okay, and thus is very nice because you have this matches with the degrees of freedom of the photon. Of the photon, which only has 2 degrees of freedom or 2 polarizations. Okay. So, this is the main advantage of studying the Coulomb gauge. Okay. It directly then it constraints. Okay, these equations, this gauge meaning fixing is like a constraint equation, right? You are constraining your degrees of meaning your choice and your degrees of freedom. Okay, it is like constraining this thing. These are like constraint equations. Okay. So, these degrees meaning, so you are constraining this, here you are putting it on the entire 4 degrees of freedom, here you are putting it only on the 3 A bar essentially on the 3 vector of the A mu. So, these are like constraint equations, and so this the advantage of choice of the Coulomb gauge is that it directly matches with the remaining degrees of freedom directly match with the physical degrees of freedom of the photon, whose physical degrees are only 2. Are only 2 polarizations. Okay. So, that is the main advantage of choosing the Coulomb gauge. Good. Then there are other gauges also like axial gauges, then there are also non-axial gauges, gauges. Okay. But we will not study it. There are huge number of gauge choices possible, and you can study the entire QED in all these possible gauges essentially, and there is a very famous book by Gastmans and Wu, T.T. Wu, who have studied QED in all gauges. The title of the book is not exactly this, but I think it is called QED in the ubiquitous photon. I think it is called the title of the book is called the ubiquitous photon. I think, if I remember correctly, it is a blue book, and this is a book which you can study if you are interested in studying QED in all possible gauges and how you relate one by another, and each of them will have different features and everything. For the present, let me just stick to these 2 gauges, and then let us move to the quantization, because now we have introduced the gauge choices, we are fixing the gauge. Now, we will now move to the quantization essentially. Okay. So, let me stop here, and in the next lecture I will look at the quantization in the Coulomb gauge and then with the Lorenz gauge essentially, and the Lorenz gauge is much more advantageous. Okay. let me stop here. Thank you very much, and hope to see you soon.